Welcome to Hubble's Universe Unfiltered. I'm Dr. Frank Summers of the Space Telescope Science Institute. In this show, we're going to be talking about our own Milky Way Galaxy. And as this diagram shows you, our Milky Way Galaxy is a barred spiral galaxy. Now, spiral is the easy part. It's this pinwheel shape, that's the spiral shape that you see of the spiral arms in our galaxy. The bar refers to this straight section here that sort of connects the two main spiral arms. Bars occur in a lot of spiral galaxies. Our location within the Milky Way Galaxy is somewhere around here, but this is just a diagram. We don't actually see the Milky Way looking like this from our point of view because we're inside this flat disk. Instead, on the night sky, we see it like this. This is the Milky Way that stretches across the entire night sky. What we've done here is we've taken the entire sky and unrolled it into a flat map to show you the whole thing. And the center of our galaxy is positioned in the center of this diagram. But the Milky Way isn't the only galaxy we can see in the night sky. We can actually see several galaxies with the naked eye. For example, this object right here, this is what we call the Large Magellanic Cloud. It is a satellite galaxy of our Milky Way Galaxy. And this object right here, well, this is the Small Magellanic Cloud, which is a smaller satellite galaxy of our Milky Way. They're called the Magellanic Clouds because Magellan discovered them when he did his around-the-world voyage. Of course, anybody living in the southern hemisphere could just look up and see them at any time in history. So he didn't really discover them, he just brought the news of them back to northern hemisphere Europe. Now, the biggest galaxy you can see with the naked eye is this one over here, and this is the Andromeda Galaxy. It is a large galaxy like our Milky Way Galaxy, and there's one more galaxy. Although you can't technically see this with the naked eye, it's going to figure in our story today, so this one right here is the Triangulum Galaxy. It's a medium-sized spiral galaxy. And these galaxies are all part of what we call our local group of galaxies. And in our local group, it's dominated by our Milky Way Galaxy and the Andromeda Galaxy as the two large galaxies. The Triangulum Galaxy is a medium-sized galaxy, and all the rest, about 36 other galaxies, are these small dwarf galaxies. And so they're distributed, well, you can see there's a bunch of dwarf galaxies near the Milky Way and a bunch near the Andromeda Galaxy. And so the distribution is, across several million light years of space. But for today's story, what's really important is not just their distribution, it's also their motion. And to help you understand how we get their motion, I've got to do a little bit of digression here. So, first of all, you know that if you take white light and you send it through a prism, you get a rainbow, all the different colors of light. So if we take the sun's light, spread it out, we get all the colors of the rainbow. But that's not true, for example, if you looked at this neon light, this pizza sign that has neon, glowing neon. If you looked at that light and spread its colors out, what you would get is a pattern of distinct lines. The neon tube, the energy from the neon atoms, doesn't come out at all the different wavelengths. It only comes out at very specific wavelengths. And that's not just specific to neon, that's true of any element. For example, this is the spectrum of hydrogen. Hydrogen has these specific lines. Now, what's really important for today's story is that they are very specific wavelengths associated with the elements. All right? And so when we look at the spectrum of a star, instead of looking like this, it actually looks more like this. We get the full spectrum, but we also have these dark lines in it. And they are dark lines because the elements are in absorption, and they're absorbing at these very specific wavelengths. So they can serve as markers in a star's spectrum. Now, these markers can change when the object is in motion. If the object is moving away from us, then the light will get stretched, the wavelengths will go to longer wavelengths toward the red end of the spectrum, and all of these markers will shift towards the red. We call that redshifted. Oppositely, if the object is coming toward us, the wavelengths will be scrunched, and the objects will move to shorter wavelengths toward the blue end of the spectrum, and of course we call that blue shifted. So by looking at these spectral lines in the spectrum of an object, we can tell whether the objects are moving toward us or away from us. We can do that, for example, for galaxies. And this is Edwin Hubble's original diagram from the 1920s when he did just that. He took all the galaxies he could measure, and he measured on the y-axis here we're showing the galaxy redshift, and on the x-axis here we're showing the galaxy distance. And what Edwin Hubble discovered, what was incredibly important, was that as you go further away from us, the galaxies appear to be moving away from us at a faster rate. This is the Hubble law. This is the expansion of the universe. We're seeing that as galaxies that are further away from us appear to be moving faster and faster away from us because the universe is expanding. Now you'll note that almost all the galaxies are redshifted except for some of the nearest ones. These are galaxies inside our local group. And in particular, the Andromeda Galaxy is blue shifted. The Andromeda Galaxy is coming towards the Milky Way. It's on its way towards us. And so the natural question has to be, are we going to get a collision? Are we going to get two galaxies come smashing together, pulling each other apart? The answer, up till now, has been a definite maybe. Let me explain why. So, Andromeda is coming towards the Milky Way, and this velocity vector represents its motion. Say it. All right? Now, the velocity vector is actually composed of two components. There is a radial component, which is coming directly towards the Milky Way, as represented by this red arrow, and then there is the transverse component, represented by this blue arrow, which is the sideways motion. Now, when we measure the motion due to the red shifting and blue shifting of the lines, we're using Doppler shift, and Doppler shift only measures the radial component of the motion. So we know that Andromeda is coming towards us, but if Andromeda has a big enough transverse motion, it might circle around us, it might slide past us, and we won't have a collision. So how do we measure this transverse motion? Well, measuring transverse motion for stars can be somewhat easy. This is a very particular star here. It's called Barnard's star. It has what we call the largest proper motion on the sky, which means that we can see its motion relative to the background stars. Barnard's star was in this position in 1985 relative to the background stars, and here's where it was in 1990. It moves over the course of a human lifetime a considerable amount on the sky. And here's where it was in 1995 and 2000 and 2005. We can measure the motion of Barnard's star over a course of a decade or so and measure the relative motion between our sun and Barnard's star. Now, what we want to be able to do is measure that same motion, but for the Andromeda Galaxy. But the Andromeda Galaxy is about 1 million times farther away than Barnard's star. So the motion would be approximately 1/1,000,000th the size of the motion of Barnard's star. That would be incredible if we could do it. And Hubble has been able to do it. Let me tell you how. Start out by looking at this very small region in the halo of Andromeda. Now, you may say, okay, but Andromeda's up here. Why are we looking down here? Because around the central disk of Andromeda, there's a large halo of stars. And if we tried to look in the disk here, well, things would be awfully crowded. But Hubble looked down here, and we got to see the stars in the halo of Andromeda. And this is the image here. And it's an amazing image, and this actually isn't even anywhere near its full resolution. Let me bring up a small piece of it at full resolution. Okay? So you can see this star here with a cross on it. That's a star in our own Milky Way Galaxy. Almost every other star in this image is a star in Andromeda. Hubble's resolution is so fine, it can see stars in a galaxy 2.5 million light years away. We can also see globular clusters, star clusters. This is not in our Milky Way Galaxy. This is a globular cluster in the Andromeda Galaxy. Also, we're looking through the halo of Andromeda, so the star density isn't that great. We can actually look through it. This is another galaxy well beyond Andromeda that we're seeing through the stars of the halo of Andromeda. So within this image, we've got a variety of objects. We've got stars in the Milky Way, we've got the stars in Andromeda, and we've got all these background galaxies. And we can use these pieces in order to measure the motion of the stars. What we're going to do is measure the stars in Andromeda, their positions extremely carefully relative to these background galaxies. Because the background galaxies are so far away, they're stationary relative, and we can see the motion of the stars in Andromeda relative to those objects. Now, how could we possibly do it when the motions are incredibly tiny? Well, we don't even have to measure the motions of even a single pixel. What we do is we measure subpixels. Let me show you what I mean here. This is a star in Andromeda, blown up really huge, so you can see the individual squares of the pixels, right? So every single square you see here is just one Hubble pixel. Now, the motion of this star over the course of a decade will be much less than a single pixel. But what we can do is we can create a mathematical function, what we call the point spread function of a star, and we can fit the profile of this light of the star. And that will give us a very, very precise center that is within pixel units, in sub-pixel units. And if we can measure the point spread function beautifully and measure the motion of it over the course of decades, we can measure the motion of the star on sub-pixel units, even down to thousandths of a pixel. They can measure the motions of these stars in very, very fine units and be able to then get the proper motion across the sky. What did they discover? Well, they found that the Andromeda Galaxy has almost no sideways motion. When you measure the tiny motions of those stars, and then you subtract out the motion of the sun within our Milky Way, we find that between the Milky Way and Andromeda, it's consistent that the two are head-on collision. The Andromeda Galaxy and our Milky Way Galaxy will collide in about 4 billion years. And from other observations, they've measured the motion of the Triangulum Galaxy, and the Triangulum Galaxy will be swinging around the pair, and actually in some cases it might actually get involved in it. They're not sure. Probably will not get involved in the collision, but it's going to still remain bound to the colliding pair. Well, this is cool, right? This calls for a computer simulation. So we took the parameters of the visualization and put it into a computer model, and from that we produced a scientific visualization of what the Milky Way and Andromeda collision will look like. The simulation begins looking at the Milky Way, because really not much happens during the beginning of it. And so for a couple billion years we'll sit here and watch the Milky Way, and then we'll pull back to show you the overview of the local group. We have the Andromeda Galaxy lower left and the Triangulum Galaxy upper left. The camera's orbiting around. It's going to circle past the Andromeda Galaxy so that you can see that it is this thin spiral disk. But those spiral disks are in jeopardy because about 3.9 billion years from now, smash! The Milky Way and Andromeda are going to pass right through each other. Those disks are going to get destroyed. We're going to pull out these big long tidal tails, and eventually the two galaxies are going to come back together again, smash one or two more times, and merge together to form a single galaxy. It's been colored yellow in this visualization here because elliptical galaxies aren't actively making stars. They're mostly old stars, which are more yellow, whereas the spiral galaxies are colored blue because they are making young stars. So you look at this simulation, and one of the first things people always ask about it is, well, what's going to happen to us? We're inside that Milky Way galaxy. What's going to happen when the two galaxies collide? Well, first thing I can tell you is you don't need to worry that our sun is not going to smash into another star from the Andromeda Galaxy. The distances between stars are so vast that the stars will just pass right through each other. Whereas galaxies, the distances between them are about 25 times larger than their sizes. Okay, so a galaxy is about 25 galaxy units away from each other. Whereas stars, compared to the size of a star, the nearest star is about 1 billion times farther away. So there's plenty of space between stars for other stars to pass through. So our solar system, the Earth's orbit around the sun, will all be fine when the two galaxies merge. What will happen is we'll get to see a really cool view of the night sky. Now, you may have seen this type of projection of Earth. This is a all-sky projection that takes all of the sky and spreads it out into this oval shape. It's called a Hammer-Atoff projection. Well, we can do the same thing for our Milky Way, and this is the visualization of the Milky Way and the Andromeda Galaxy and the Triangulum Galaxy, and we can watch it as if we were sitting at the point where the Sun is today within the Milky Way. Now, you know that the Sun is actually orbiting the center of the Milky Way. But if we tried to do this visualization with the Sun orbiting the Milky Way, everything across the sky would keep moving and it would be kind of hard to watch. So what we did here is we took the Sun's current position in the Milky Way relative to the center of the Milky Way, and we kept the camera fixed there. And then we wanted to see what the night sky might look like as we go into the future. So here's the visualization. And you can see the bar of our spiral galaxy orbiting around, and you can really see that it has a barred shape as things go. For the first few billion years, not really much happens. You can see the Triangulum Galaxy moving away from the Andromeda Galaxy, and you might notice if you look carefully, the Andromeda Galaxy slowly getting bigger. And it keeps getting bigger, and it keeps getting bigger because it's coming straight towards us. And round about 3 billion years, it starts to take up a pretty large chunk of the sky until finally it swoops and crashes through. This is the view from inside the galaxy of the collision. The Andromeda goes away and then comes back for another pass. And finally, you can see the merging effect that happens when the two galaxies finally become one about 6 billion years from now. You can see the Triangulum Galaxy just orbiting around the merged pair as it moves across the night sky. That is a visualization of what our really, really distant ancestors might see in their night sky. We're going to start out with the Milky Way and Andromeda as we see it today. Andromeda is going to grow really big on our sky. We're actually going to have like 2 Milky Ways in the sky at some point. And then it's going to pass through us, and then it's going to merge. Now, this is just visualization. This is a computer simulation. We've got some really good artists in this building, and we can take this one step further. So here is the night sky as we see it today, the plane of our Milky Way and Andromeda. And you go a few billion years into the future, Andromeda is going to get kind of huge. And then Andromeda is going to come crashing through, being the time when we're going to see essentially 2 Milky Ways on the sky. And when it comes crashing through, we're going to have an amazing display on the sky, because as galaxies crash together, stars erupt. And see all these red star forming regions, there's going to be incredible amounts of star formation as the 2 galaxies pass through. Andromeda is then going to distort, we'll develop those big long tidal tails as it moves away from us. And then the 2 galaxies will come back in and finally merge together. About 6 or 7 billion years from now, we will look out upon an elliptical galaxy. Now, as I said, this is a possibility of what we might see. The truth is, we probably won't be able to see something that beautiful, simply because our sun, in its nice orbit around the Milky Way Galaxy, is going to get kicked out of that orbit. Our sun will probably get thrown way out into one of those tidal tails, or else it will go way down into the center. So our view will not be as nice and beautiful as we've shown it here, although I gotta say, this is some really cool illustrations. So, when you look up at the night sky, you can see our Milky Way Galaxy. You can see the large and small Magellanic Cloud, but the most distant object in the night sky that you can see is the Andromeda Galaxy. And it's located in the constellation of Andromeda, which is somewhat recognizable if you can find the Great Square in Pegasus and work off of the stars in the Great Square in Pegasus. This star right here is the corner of the Great Square in Pegasus, and if you go out in Andromeda 2 stars and then go up a bit, you can find the Andromeda Galaxy. And it is amazing to look out at the night sky and see an object that's 2.5 million light years away, the most distant object that you can see. But remember, it's headed straight towards us. Thanks for listening. We'll see you next time on Hubble's Universe Unfiltered.